Sometimes we're faced with integrals that can look both complicated and quite daunting. We can use a substitution to make our work easier. In the last video we looked at integration by recognition. In all of those particular examples we could have used a substitution. When we're using a substitution we transform the original integral in one variable, say x, to an integral with respect to another variable, say u, where u is a function of x. So let's go back and look at some basics. When we first looked at integration, we saw that we could write y is equal to the integral of the f of x dx. So when we were integrating, we met this particular notation. If we're using a substitution, we can write now y would be equal to the integral of the f of x multiplied now by du dx, and we would integrate this with respect to u. If you want to see how this is formed, please check out my site and have a look at the video on the chain rule. So what we're going to do, we're going to employ this and work through a couple of fairly straightforward examples. So now let's look at the integral. Let's go for x multiplied by the root of 1 plus x. We would have this integral now, and this would be with respect to x. We would be given a substitution, so we could say let u be equal to 1 plus x. Now, the way in which you carry out this substitution right here is entirely up to you in terms of the order. The order I like to do is to consider now this function right here. What we're looking for is a substitution for dx. So I'm going to take this equation right here and differentiate both sides with respect to x. If I do that, differentiating u with respect to x will give me du dx. Differentiating now 1 plus x with respect to x will give me 1. Therefore, I can now say that du will be equal to dx. I'm going to gradually transform this integral with respect to x into 1 with respect to u. When you're doing this, it doesn't have to be this laborious, but I want to show this step by step. And at sometimes it won't make an awful lot of sense. So what we're going to have then is the integral of x multiplied by the root of 1 plus x. I know that du is dx, so I can now write du. Consider that u is equal to 1 plus x, so the next move I can make is the integral of x multiplied by the root of u. 1 plus x is u, I can sub this in. So gradually I'm transforming this now into an integral with respect to u. If u is equal to 1 plus x, then u minus 1 is equal to x, and I can now sub this in just here. So I'm looking now at u minus 1. Now at this stage I'm going to write the root of u as u to the 1/2, and now I'm integrating with respect to u. So this now is fully in terms of u. I've got a fairly straightforward integral from here. Using simple rules of indices, u times u to the 1/2 is u to the 3/2, minus now u to the 1/2, and we're integrating with respect to u. So if I do that, I'm simply going to raise by a power and divide by the new power. So this will become 2 over 5 u to the 5/2 minus 2 over 3 u to the 3/2, as we've seen now with our basic work with integration, and then we bolt on a constant of integration. This is in terms of u. I want the expression now in terms of x. So all I'm going to write then is 2 over 5, the quantity 1 plus x to the power of 5/2 minus 2 over 3, the quantity 1 plus x to the power of 3/2 plus a constant of integration. And that is now my integral. Okay, so what I've done, I've transformed it now from an integral with respect to x to 1 with respect to u, and then put it back together. Now, if we were asked to find a definite integral, let's put some limits on here, from 1 to 2. At this stage, now, I could simply put the values of 2 through and subtract away 1. Alternatively, I could have left it now in terms of u. So if I wanted to evaluate this, considering that u is equal to 1 plus x, I could actually look at the integral with respect to u by subbing these in, and you will need to show this in the exam. If x is 2, then u is 1 plus 2, that's going to be 3. If x is 1, 1 plus 1 is 2, so there I could evaluate now in my expression here, obviously taking the c away if it's a definite integral, subbing in these two limits. Either way round you'll get exactly the same answer. So if you put in this one now 3 and 2, or if you like, if you want to put it just here and get rid of the c and have 3 and 2, that would be the same as doing it from here now to the 1 and the 2. So that is essentially going to give us the same answer. But if you're just asked for an indefinite integral, you put it back in terms of x. If you're asked to evaluate, you have the choice. So that's a nice straightforward example. Let's look at another one. Let's look at something slightly more challenging. Let's go for the following. Let's say that we've got now the integral, and let's go for x multiplied by the quantity. Now 3 plus 2x. We'll raise that to the fifth power. We'll integrate with respect to x, and we will let u be equal to essentially this inside function of 3 plus 2x. So what I'm going to do is simply transform this. If you want to hit pause and have a go at it, you're welcome to do so. So my first move, du dx. Okay, differentiating both sides of this equation right here with respect to x. That's simply going to leave me now 2. Now at this stage, what I can write is the following. I can write du is 2 dx, or I can write 1/2 du is equal to dx. That really depends on your mindset, how you want to see that. Now if I make this transformation, I can now write with the constant, the other side of the integral, I can write this as 1/2 x. Then we're going to have 3 plus 2x to the power of 5 multiplied now by du. So all I've done is made that substitution. 1/2 du is dx. So I've made the substitution. You certainly don't have to view it that way. So let's go ahead now and manipulate this. So what I've got then is the following. I've got 1/2 the integral. Now we've got x here. So if we consider that that's going to be 1/2 the quantity u minus 3. That's what x is going to be. If we just look at this right here, now, if u is equal to 3 plus 2x, then 1/2 the quantity u minus 3 is equal to 2x. Just rearranging that. So what I've got then is 1/2 the quantity u minus 3 multiplied here. Now this is u, so I can write now that this is u to the fifth du. So yet again, taking my constant, the other side of the integral, I've got 1/4. Now the integral, and expanding this bracket, we can just expand this bracket and do it term by term. We will get u to the power of 6 minus 3u to the power of 5 du. So what I'm going to have then is 1/4 the quantity. This is going to give me 1/7 u to the power of 7 minus now. And if I raise this, that's going to be 6, so that's going to be 3/6, so that would be minus 1/2 u to the power of 6 plus a constant. Now, at this stage, I could factor it and make my life a lot easier. So if we consider if I took 1/14 out of this, then that's going to give me now, and I'll write this here, let's take 1/14 out, we're going to get 1/56. I can take u to the 6 out, and that's going to leave me now with 2u, so let's just write this here, 2u minus 7 plus a constant. That is one way that I could have written that. And the only reason I've done that is to show you that often these are factored. So just check my factoring, 2 minus 7/14, take the 14 out and take a factor of u to the 6 out. Now this will allow me at this stage or this stage to put now u is back in as it was. We know that u is 3 plus 2x. So we can say that this would be 1/56 now, and we know that u is 3 plus 2x, so we've got 3 plus 2x to the power of 6 multiplied by 2 lots of 3 plus 2x minus 7. Now you certainly don't have to do this like so. I'm just now showing how well or how easily or how far this can be factored. This is not part of a technique, it's just manipulating algebra. So what's that going to give us? That's going to give us 1/56. We're going to get 3 plus 2x to the power of 6. Then we're going to get, that's going to give me 4x, and then we're going to have minus 1. So 4x minus 1 plus a constant. So if you want it in terms of x, you may be asked to show that the integral now of this can be written in this form right here, and that's just one of the ways it could be written. You're not always going to have to do that, but it may be asked of you. Okay, let's look at another one. Let's go for the integral of sine cubed x dx. So this time, in the last video, we saw that if we had now the derivative multiply this, we could do it by inspection. What we're going to do this time is let u be equal to cos x. Okay, so focusing here, I'm going to have now du dx, differentiating both sides with respect to x, is minus sine x. So at this stage, I've got a couple of choices. I can say minus du over sine x will be equal to dx. Now that isn't mandatory, but it may help you. So let's go ahead now and work with this. What I've got now is minus the integral. This is a constant, this is minus 1. I've got sine cubed x du over sine x. So consider now I'm looking at the integral of minus sine squared x du. All I'm simply doing now is cancelling off. So let's consider u is equal to cos x. We know cos squared x plus sine squared x will be equal to 1. Therefore, what we can say from here is that sine squared x will be equal to 1 minus cos squared x. Therefore, we can say sine squared x will be equal to 1 minus u squared. Cos x is u, so u squared is what we've got. Now I can sub this in. So I might have done this a different way to avoid these negatives, but essentially I'm now looking for the integral, negative the integral of the quantity 1 minus u squared du. So just rewriting this, I'm looking for the integral multiplying through, we're going to have u squared minus 1 du. So nice straightforward integral at this point. All we're going to have then is 1/3 u cubed minus u plus a constant. Now we know that u is cos x, so we have 1/3 cos cubed x minus cos x plus a constant of integration, and again you could factor that if you wished. If you wanted to factor it, we could take out 1/3 cos x. That would leave me now the quantity cos squared x minus 3, and then our constant. And that is another way that you could write that. So there we go, that's essentially another example of that one. Okay, let's go on and look at something slightly trickier. Okay, let's go for this one. Let's go for the integral now of sec to the 4th x, and then we'd have dx, and we'll let u be equal now to, let's go, u is equal to tan x. Now from here what we can do is say the following. We can say that du dx, differentiating both sides of this equation. Remember, we're trying to let this be in the form y is equal to the integral now of the f of x multiplied by du dx, and then we're integrating this with respect to u. That goes back to where we started. So du dx, the derivative of tan x, is sec squared x. Okay, so at this point we could say now from here that du, and we can write this du over sec squared x, so sec squared x is equal to dx. I like to split this up. You certainly don't have to. You could simply multiply it and then make a substitution. So what I like to do now is write that this will be sec to the power of 4, or sec to the power of 4x, and now we've got du over sec squared x. Now that's going to cancel. So I can say that this is going to be the integral of sec squared x du. So let's deal with this. Now we know u is equal to tan x, so let's use a trig identity. Sec squared x is equal to tan squared x plus 1. Sec squared x therefore will be equal to u squared plus 1. So all I'm going to do is sub that in, and now I've got the integral of 1, or u squared plus 1, u squared plus 1 du. So I'm going to go ahead and integrate this. So this is going to give me now 1/3 u cubed plus u plus a constant. So very similar to what we had before. Now we know that u is tan x, so all we're going to do is put 1/3 tan cubed x plus tan x plus a constant of integration. So that's what we've got, and we can simply go ahead and do that. So there we go, 1/3 tan cubed x plus tan x plus a constant. Okay, let's move on. Now, earlier on in the video I said that we could alter the limits. what we're going to do is look at an example now. We'll take the integral from 0, let's go from 0 to 5. Let's go from 0 to 5 of x multiplied now by the root of x plus 4 dx. Okay, now in this one, we're not given a substitution. I'll just write now that let u be equal now to x plus 4. So what we're going to have then, quite clearly we can see that du is going to be equal to dx. Okay, hopefully that now makes sense. Du dx is going to be equal to 1, therefore du is equal to dx. So I'm going to gradually transform this, and for a while the limits are not going to seem we're not going to make an awful lot of sense. So we've got now 0 to 5, and what we're going to have then now is u minus 4. So u minus 4 is x, multiplied now by u to the 1/2 power. So I'm now assuming that you're quite comfortable doing what we were doing earlier. And that's going to give me now with respect to u. Now at this stage I'm going to change these limits. So if we consider that this now is going to be u is equal to x plus 4, then what we're going to have here is the following. If x is equal to 5, we can say when x is equal to 5, we can say now u will be equal to x plus 5, which is 9. When x is equal to 0, which is this limit right here, then u is going to be equal to 4. So now we're looking at the integral. We've changed the limits. We need to clearly state that we're going to change the limits. So I'm going now from 4 to 9. So I've got now u to the power of 3 over 2 minus 4u to the 1/2 du. So now I'm going to now evaluate these limits once I've integrated. So we're going to have now, that's going to give me 2 over 5 u to the power of 5 over 2 minus now we've got, and we're going to raise this by a power and divide by the new power. So I'm going to get now, if we consider, and I'll just write it out, we're going to get minus 4, then we're going to get, so we're raising by a power, dividing by the new power, so that's 2 over 3, now u to the 3 over 2. Okay, and we're now interested in this from 4 to 9. So we could go ahead and evaluate. Now, alternatively, what I could have done when I did at this stage, I could have just left the limits alone and now put this in terms of x. It wouldn't technically make sense here, but if I switch this back, what we would have now is 2 over 5, and we know that this is the substitution of x plus 4 is u. So I'd have x plus 4 to the power of 5 over 2 minus 8 over 3 x to the power, x plus 4 to the power of now 3 over 2. And I would simply evaluate the limits on this one to the original one that I had. So we'd have 5 and 0. Now to me, this one is easier given what we've got here. So for example now, if I subbed it in here, that would be nice and straightforward. That would give us 9. The square root of 9 is 3. 3 to the power of 5 is 243. So if we did this one, we'd get 2 over 5 lots of 243 minus that, and if I put 5 in here, we're going to get this now cubed. So if I put 5 in there, that's 9. Square root of 9 is 3. 3 cubed is going to give me 27, so that's going to give me minus 72. I'm kind of working this out a bit in my head, so hopefully you can see what I'm doing. And then we're going to have that, so let's just write that there. So all I'm doing is evaluating, and I'm assuming that you can evaluate these. And then we would evaluate for 0, so we'd take this away. Now from here I'd have 2/5, and if x is going to be 0, then I've got the square root of 4, which is 2. 2 to the power of 5 is going to give me 32, so that would be 64 over 5. And then we would have now minus, and if I put it into here, that's going to give me 8, that would give me 64 over 3. I'm kind of winging that a bit. And then you could evaluate that and find out what you've got. With this one, you would put it in. It's entirely up to you. So this way round, you could evaluate it. Either way round, you're going to get now the same answers on those. So we've shown that we can put it in terms of x, or we've shown that we can put it in terms of now u. So on that, it's entirely up to you. I'll let you evaluate that, given you can either do it in terms of u, or you can switch it back and do it in terms of x. Okay, let's actually do one in full, rather than just sort of talking my way through half of it. Let's go now, we'll take the integral from 0 to pi by 3. Let's go from 0 to pi by 3 of sec x. So let's say sec x tan x, and then we'll multiply this by the root of sec x plus 2. Now in this particular one we're not given a substitution, but if I let u be equal to sec x plus 2, quite clearly that's what we're looking for. We're looking now to express this as u to the half. We know the derivative of sec x is tan x, and that will give us now the product right here. So what I can say then is just here, du dx is equal to sec x tan x. The derivative of sec x is sec x tan x. So du over sec x tan x, and we'll write this just here, will be equal to dx. So you could have written now that dx sec x tan x is du. So if you like, you can write that that part is just going to be u. So your alternative here, and potentially so, we can say du is sec x tan x dx. This is probably easier to now make this substitution. As stated, it's entirely up to you. So what I can actually write here is the following. We've got the integral, and again, the limits don't quite make sense at the moment, and we can change those as we go. What we've got is sec x tan x dx. Well, that's du. So I've got the root of sec x plus 2 du. So I know that u is sec x plus 2. So I'm now looking at the integral of u to the 1/2 du. Now I'm going to change the limits here. Now what we've got here is the following. We've got pi by 3 and 0. So we kind of need to know, if we're going to swap these over, what that is. So if we look at this, sec x, let's say now that x is equal to pi by 3. If x is equal to pi by 3, sec of pi by 3 is 2. Cos of pi by 3 is 1/2, so that's going to be 2. Sec of pi by 3 is 2. And of course you can evaluate this on a calculator. When x is equal to pi by 3, therefore u is going to be equal to 2 plus 2, which is going to be 4. If x is equal to 0, if we consider now sec of 0 is going to be 1, so therefore we can say that u will be equal to 3. If you're unsure, just put these through a calculator. Sec of 0 is going to now give us 1. So that's what we'd have. So what we're looking for then now, I've changed this, and we're going to have then, instead of pi by 3, we're going to have 4 and 3. So I'm going to have now, if I raise by a power and divide by the new power, I'm going to have 2 over, in fact, let's just rewrite this, u to the 1/2 du. Okay, let's go ahead and evaluate this. So I'm going to now get 2 over 3, u to the 3 over 2, and we're interested in this now between 4 and then 3. So let's go ahead and sub that in. So that's going to give me 16 over 3. And then we're going to have now, what's that going to be? 3 root 3. So that's going to be 2 root 3. So minus 2 root 3. And I'm kind of blagging that a bit in my head, doing the mental calculations. But if we take the square root of 3 and then cube it, that's going to give me now 3 root 3. 2 over 3 lots of 3 root 3 is going to give me minus 2 root 3. So let's just check I've done that right on the calculator. Okay, let's grab it up. So if I do now, I'm kind of confident that's right. I don't know why I'm thinking otherwise. So what have we got? Times by now. So that's going to be 3 root 3. I don't know why I'm moaning about that. There's 2 root 3. And you can put that in and find that. So that's what we would get. Now, at this stage, that's now essentially the exact answer. So all I've done is evaluated using my rules of indices. So if we wanted to, we could have actually put this back in terms of x. So what we'd have here now is the following. We'd have 2 over 3. Now what I've got is the following part here. I've got u is equal to sec x plus 2. So I'd have now the quantity sec x plus 2 to the power of 3 over 2. And I'm going to consider this now, and we're looking at this from 0 to pi by 3. Now if I sub in here pi by 3, we've already seen now that that is going to give me, sec of pi by 3 gives me 2. So I'm going to have 2 over 3, and then I'm going to have 4 to the power of 3 over 2. And then if I subtract away, subbing this in, and again I'm assuming you can evaluate the limits, minus 2 over 3. Sec is going to give me now, sec of 0 is 1, so that's going to give me 3 to the power of 3 over 2. By subbing this back. So we know the square root of 4 is 2, 2 cubed is 8, 2 times 8 is 16, 16 over 3, and then we're back with the same scenario just here, which is going to give me minus 2 root 3. So we can see that we can evaluate it in terms of u, and I have rushed that bit, I apologise on that part. But essentially you can see that you can switch it back and switch forward like so. So there we go, integration by substitution using some basic examples. And later on we will look when we've got more complicated functions where we use a substitution again.